Alright, so here we have Banggood Item 1063307. We'll do a quick unboxing here. Comes with a USB to barrel power cable. This is a, what they call it a frequency tester, but it's a frequency counter. We have an LCD display, a PIC microcontroller in its socket, its various components, a clear plastic shell and the circuit board, and some instructions for it. And for those of you who don't know what a frequency counter is you feed a frequency or an oscillating signal into the input, and it will read out what the frequency is. So say you feed it a 1 kilohertz tone, it will tell you 1 kilohertz up here on the readout. Speaking of which, let me turn on my frequency generator so it can start warming up so it's fairly accurate once we go to do the test. What did you post? Mike, that one's borderline. I'll let it go though. Anyways, back to this. So what do we got? We'll leave the case for last, obviously. We'll look at the instructions here. Okay, we got our frequency. Okay, so this is our capacitor values, welding instructions, debugging, and then how to use the measuring. Whether you're doing it for a crystal oscillator or an outside source. Okay. So, again, okay, I won't need this. I already put the solder paste away. I've already turned off the hot air gun because this is all through-hole components, so instead of SMD work. Again, I've probably had this one on my pile for a while. Let's start getting out components. That's a nice little Ziploc baggie. We'll set it aside. Alright, we got jumpers. We got the little thingy that goes on the jumpers. We got screw terminals. We got a 58005. This is a NPN transistor. There should be a second one of these. 58805. There's our other NPN transistor. I'm just going to try to straighten the legs a little bit here. And we got, this is a 7550 version A. This is a 5-volt regulator. We got a power in jack. I got a single resistor by itself. I got a bunch of capacitors here. I got some hardware. That's for putting the case together. I got some roll pins for testing crystals. I've got the actual crystal for the device. A cap for the button, we'll put that over there. Let's see, we got a 104. A 104. 22, a 22, it's probably another 22, yep. fourth 22. Those are 22 picofarads. Yep, and I should have 4 of them. I have a 102 picofarad one. And then 2 104s. Okay. I should be marking these off. Alright, so I've got the crystal. I've got the push button switch. I got the 2 104s, the 102, the 4 22s. I've got the voltage regulator and that. I have the LED display. I have the microcontroller. I have the DC power in jack. I have the roll pins. I have the signal wire. I have the jumper thing. I have my diodes here. I have 1, 2, 3, 4, 5 diodes. Let's see. Okay, so I should have one 100K resistor, which is probably this guy. $99K, close enough to 100. These are the 10K. Just making sure. I could sit here and decode the bands, but I'm being lazy. And those are the 1Ks. Okay. Okay, so I have the 100K. I have the 310K. And then how many is that? 6, 7, 8, 9, 10, 12, 13. 8, 9 of those. 1, 2, 3, 4, 5, 6, 9. Alright, we have all the pieces and parts, so that's a good start. Alright, so we'll slide these off to the side. Get in here with a soldering iron. Try to think of this logically so I don't like drag half this stuff across my desk. Ours. 102. Those guys. That guy. Power jack, put that up there, move all the 22s over here. Diodes there, that there, those there. So I'm going to start with the diodes because those are the smallest. That's one of the 1Ks that escaped. Okay. And I moved everything over to this side because my soldering iron's on this side, so I won't drag my the lead of my soldering iron through my components. so where does diode 1 go? Okay, diode 1 goes there, and then 2 through 5 go there. And the black band on the diode goes to the line on the circuit board. Okay. Pliers for bending. Soldering iron is up to temp. Now, if you're wondering why I bend these with a pair of pliers, is because then I put less stress on the actual component, which for a resistor probably isn't that big of a deal, but for these glass diode packages, you can actually crack the glass and make the thing not work. Really, what I should get is I should get one of those little bending tools. They sell them on eBay, and I think Banggood has some, and they sell, they sell them on Amazon, or if you have a 3D printer, Thingiverse has a model for it. I mean, you just put the component in and blink, bend over, and it's done. Uh-oh, we've got a loudly doofing spoon in chat. Careful, Spoon, you might summon Jinx. Piece of solder I've been working off of, trying to get rid of it. That's a lot of zeros. Well, if you want us to just summon Jinx, summon Jinx. I'm sure he'll show up eventually. Although I don't know what time it is in Germany. What is it, 7 a.m. there? Or am I off an hour? I was going the wrong direction. I was subtracting 7. I should have been adding 7. on, you. Okay, what I did is I just tacked one side of each of the diodes down. Made sure they're all flat and flush against the board. Now I'm going to solder the other side. Oh, I need to get my cup of cutoffs here in a second. Okay. Make sure I got nice penetration through the through holes. I did. Get my cup of cutoffs, which is getting rather full. I might have to get a bigger cup. Yeah, Willspin. I like Winamp. I used to use it because I like the skins, but I haven't found any real good skins that work well on stream. Let's look here, Spoon. Now, mind you, I am still running the pre-AOL version. I'm running 5.6, which is the version just before AOL took over Nullsoft. Yeah, let's see here. So yeah, I'm trying to see where it was in here that it used to say that. Yeah, I can't remember where it says that in there, but it's in there somewhere. But again, like I said, I'm running the last version before AOL took over and put all of their spyware in it. Which I guess wouldn't really matter all that much anymore because AOL no longer exists pretty much. I think they've been absorbed by Time Warner Cable, wasn't it? Mitch, if you're a Time Warner Cable owner or customer, they already know everything that you're doing anyways. Oh, it's all AT&T now? Okay, well, yeah. Alright, so diodes are in. Next comes resistors. So the 100K is resistor 1. Which this is the 100K. This is the 100K. Again, we'll bend the leads down nicely with a pair of pliers. And stuff it in resistor 1 slot. Didn't quite bend it enough. Take it out. Straighten all this out. See, I unfortunately am dealing with all that Comcast crap that goes on, but I'm not directly using Comcast for my internet. I am using Cox Communications, which is a sister company of Comcast. They're two separate entities but use the same backbone hardware. Okay, my 10Ks are resistor 2, resistor 3, and resistor 5. Yeah, Comcast and Cox Communications partnered with one another to provide each other with backbone in areas where the other wasn't. And so anytime something screwed up happens with Comcast, it happens with Cox Communications. I'm surprised I'm actually still streaming, tell you the truth, because I probably have gone over my data cap for the month. That was resistor 3, right? Yeah, that's resistor 3. 9 and 2 and 5. Where is... Where's resistor 2? Yeah, resistors, it doesn't matter which way they go in. I generally do them all the same direction because I'm just that way, but they're not polarity sensitive. But I always tend to put the starting band either that way or up, depending on which way the resistor's oriented. Just a personal preference that I do. Oh yeah, and don't get me started on CenturyLink, those buggers. They convinced me to switch over to them because they were gonna have fiber fast internet. Well, what they meant by that was it was gonna be fiber to the local node and then regular copper to from the node to my house. Which you think that wouldn't be bad, considering the local node is about a quarter mile down the road, so not very far from my house. But the copper from there to here was put in the 80s. So I was getting, what was it, 760K down. And the only way that they could help me was if I paid them $2,000 to run a new line from the node to my house. To their demarc on my house. And now they've taken me to collections because they say I owe them money still. And I'm just like, you know, screw you guys. I paid my last bill and I turned in all my equipment. I have receipts for everything. But evidently there was like a $2 something fee on my account that is now racked up to over $60. So they sent me to collections. You know what? Why am I not holding this board with my little helping hands while I stuff components in it? Oh, but, you know, Cox, I actually had to laugh at them the other day because they were trying to sell me on buying a bundle because I don't do television. I only do internet. And I asked them if if I increase my internet speed, will that up my monthly data cap? And they're like, no, but having faster internet will mean you use less data. And I face palmed. No, dear. A faster internet speed just means that I reach that data cap faster. Yeah, I'm all Netflix and Amazon Smile, or not Amazon Prime Video. The only reason I have Netflix is because it comes free with my cell phone. Because I have T-Mobile and I've had T-Mobile for God knows how long. But I'm on that the unlimited family plan that comes with the free Netflix. You and Mike would get along great there, Demensis. I think I pronounced that right. But honestly, the majority of the time I'm either watching somebody on Twitch or on YouTube. And then if I'm driving around in a car for work, I'm listening to podcasts. So the current one I'm stuck on right now, they actually have a channel here on Twitch. It's Geek and Sundry, the Critical Role podcast. It's a bunch of geeky voice actors playing Dungeons and Dragons. I'm a little behind. I'm only on episode like 50 of season 1, and they're on like episode 80 of season 2 already, so I'm a little behind. I think there's 117 episodes in season 1. But again, that's a podcast not for everybody. You have to like D&D in order to watch that one. Or listen to it as I'm doing. Okay, all the resistors. Come on, there. Now, no, this one's being... didn't quite want to fit. There we go. All the resistors are in. Carefully flip it over so I don't lose any of them. Oh, and for you new guys that showed up, I did this one earlier. This is another Banggood item. It'll be up on my YouTube channel. For the assembly of that guy. I am noticing that the sensitivity isn't very high on them. But then again, that is what goes to my that is the audio that goes to my headphones, and I have myself turned down in those so I don't hear myself talk as much. I'm there just enough that I know that I'm still talking. So again, just tacking down one side of the resistors. It over, making sure they're all still flat against the board. Gotta do a little bit better penetration on that one, I'm seeing. On both of those, actually. Much better. Because what you want is you want a little bit of a dome on this, you know, a little bit of a taper up onto the lead, but you also want it to come all the way through the through hole and start doing that on the other side as well, but not an excessive amount. But as I was explaining to Malfunction Mike earlier, I just did the math. I have been doing this for about, I've been soldering for about 23 years, so at least surface mount soldering. Or I mean, through-hole soldering. Surface mount soldering, I'm relatively new to that, and I'm still learning tricks and techniques to doing it. My latest trick seems to work pretty well as long as it's not on a button or anything with a plastic housing. Yeah, you guys that just recently showed up, yeah, you missed it. I melted a button with my hot air gun. And I gotta quit doing that. I gotta remember, I gotta keep up here, otherwise you guys can't see me soldering. But yeah, the general technique that I've always used is you just put the component in, put this against the hole in the lead, and then just tap with the solder. What am I doing? My soldering station's back there. And then again, like I said, you just want to make sure that it got through the through hole fine. It looks like it did. So now I got two. Trim off these. And that's the thing, when you're trimming the leads, don't cut into the solder. Because that can cause the solder joint to crack, which will cause bad electrical connections, which will cause hours of troubleshooting later for you. I mean, it's a simple fix if you crack it, you just have to reflow that joint, but Still, everything can look fine, but it'll be cracked and it won't work very well. And then you'll reflow it and suddenly, oh hey, it's working. Now me personally, like you see, I've got this little cup here that I've been putting all the trimmings in. Every once in a while I'll need to, you know, like in repairing a board, I'll need like a quick little jumper wire, or doing something, I'll just need this short little piece of something. So that's what this is just, it's a bunch of leads that I have chopped off, and I just keep them around in case I ever need them. Alright. Next up is probably going to be this little ceramic capacitors. Well, wait a second. How tall are they in comparison to the crystal? About the same size as the crystal. So, we'll do the crystal next. Just drops in there. Click it down. I'll flip it over. On there. Make sure it's still flat on the board. It is. And again, like I said, what you do, put your tip up against the hole and the lead of the component, and then just tap the other side with the solder, and it should just suck it right in. And the goal on most things is transfer as minimal heat to the component as possible, which is why I keep my soldering iron at about 275 Celsius. This solder melts at 225, I believe it is, but I like to do it at 275 because then I'm quicker and less heat gets into the component. And the less heat that gets into the component, the less likely you are to damage said component. Alright, so we've got C1 and C7 are the big boys, the 104s. So C1 and C7. It's part of the power regulation circuit. Again, these ceramic capacitors are not polarity sensitive. Now, if I was using electrolytics, they would be. But I always like to face them the same way. Oh, I completely did that by accident, but I did it the right way. The crystal, it also has the frequency printed on it, and I always put it right side up, essentially. So C1 and C7 are the 104s. C6 is the 102. We're over here. And then the rest, so C3 and C2 are the 22. And so are C4 and C5 for the oscillator circuit. It looks like this PIC micro is running at a whopping 20 megahertz. Wow. That's a speedy speedy chip. Half of you probably don't even remember computers that were slower than a gig. tip a little bit. And again, only tacking down one side at this point. Couple that are sticking out further from the board than they should, and they're crooked, so you just kind of put your finger on them and heat up that one side and just kind of straighten them out. Now, electrically speaking, this part doesn't matter, because electrically they will still work even if they're crooked. I mean, I could stand them up off the board all the way, you know, the full length of the lead, and it'll still work. They just don't look nice that way. Well, Spoon, it's a PIC microcontroller. It's an 8-bit microcontroller. It's not even a... No, it's not even in the 16-bit realm. But it's using its external crystal... it's using an external crystal oscillator, I'm assuming, to get the accuracy needed to be a frequency counter. Which we'll find out when I get this done being put together how accurate it is, because my function generator is actually, it is, okay, yeah, my function generator is locked on its oscillator, so it is up to temp. Which, that's one thing, you guys, if you have test equipment, well, that's a good thing. Speaking of test equipment, let me turn on my... No, because wasn't an abacus like 10 or 12-bit? But yes, that is a very good thing, Lady G, if you can get rid of that. But yeah, for any of you guys with test equipment like oscilloscopes and function generators and all that stuff, let them come up to let them sit and run for a little while and come up to temp before you start doing your test, because the internal temperature of the components can actually cause skewed results in your tests. Especially like a frequency generator. Because its oscillator has to get to a stable temperature, especially if it's a temperature controlled oscillator. Now, this one is a El Cheapo, so I don't know. I've not taken it apart. I don't know if it has a temperature controlled oscillator in it, or if it's just a regular crystal oscillator. But then again, I didn't get I didn't get it for high precision. I got it because it was given to me for free by a friend. She used to do electronics repairs, and it was the one in her shop. But she didn't need it anymore, so she gave it to me. Let's see, is that going to be taller than the button? Yes, that is going to be taller than the button, and that is going to be taller than the chip socket. Well, I'm hoping for you, Lady G. Alright, so I need the chip socket. Now, it's nice that they package this stuff separately because the leads tend to get bent on this kind of thing. Now, chip sockets, what I always do on these is I tack down one corner, press it down against the table while it's still hot, and then tack down the other corner, flip it over, and make sure that it is flush against the board. And then go to town soldering. And again, just touch the pin in that, feed in some solder. Touch the pin in the pad, feed in the solder. Touch the pin in the pad, feed in the solder. Rinse, lather, repeat. Rinse, lather, repeat. My solder stick's getting a little short. I might have to actually get another piece. Okay, the socket's in there nicely. Clean off the tip. Just the tip. Alright, now we'll put the push button in, because it seems to be the next highest component, surprisingly. We're not going to use a hot air gun on this one though, guys. I'm not melting this one because I don't have a replacement this big. Now, a lot of times with some of these components you can get away with not trimming leads. Like that socket does not need to be trimmed. However, the button does slightly, but there's not enough to worry about. Trying to catch them and put them in the bin, because there's just not enough of them there. Okay, now it's going to be my voltage regulators and transistors. With these, I just like to kind of bend the outer ones at like a 45 and then bend come down a little bit and bend them back straight, because they look nicer in the board this way. Just try not to bend them too much, because you will break leads off if you bend stuff too much. Now, U2 and U3 are the transistors. So, if you look on the circuit board, it's kind of hard to read with this camera. I really need to get that new camera set up. But there's a flat side and a round side on the outline printed on the silk screen. So you just kind of match the flat side of the transistor with the flat side on the silk screen. Do the same with the voltage regulator. I'm guessing the voltage regulators in case you feed more than 5 volts into this system, and I just flipped it over and they all fell out. Again, just soldering one lead of the component on first. And I think it's time to retire that piece of solder. And then again, this is for aesthetics. I make sure they're straight. This one's all cockeyed and weird. Okay. Yeah, I'm not going to try to that with that. That's gotten too short. But that's okay. Solder's not a big deal. I have plenty. Oh, and I finally used enough that I've gotten all the tangled up stuff off of it. I dropped this spool of solder probably about a year and a half ago, and it was just a mess. I finally used enough that it's down to a normal spool again. Okay, those are all down and nice. Trim the legs off. My next tallest, which is taller. Oh, the crystal tester roll pins were shorter. That's gonna be fun. See, this is why you go from shortest component to tallest component, because I missed a component and now it's like gonna be fun to get it soldered in place. There we go. Ow, hot. Those pin sockets transfer heat quite well. Okay. How tall are these? Those are probably shorter, or this is probably shorter. Yeah, I probably just did that taking it out, but I bent some of the pins. Best I can. Alright, so dots go down. Come on, go in. Go. Yeah, those are that's about the same height as the transistors. Okay. Again, on this one, we'll tack one down. Hasn't really moved. solder the rest. That one didn't get a lot of solder. There we go. It's nice and flat against the board still. And the tip. These cutoffs I probably won't worry about saving because they're really short. But I also didn't want to leave those as long as they were. Okay. There's that. Toss those in the garbage can. Let's see. That and that are about the same height. How about this guy? That guy is shorter. So he'll be next. So a little pin header for the jumper. Again, rinse and repeat like everything else. That's multi-pin. Tack down the one pin. Make sure we're flat against the board. And then solder the rest. And the tip. Flip it over. We got the power and the signal input jacks are all that's left. So again, this isn't a bad little kit. It has taken me just under an hour so far to solder it together. There's still the outer casing to the shell to assemble. And of course cleaning, because the solder that I use it's old enough that it has picked up dirt and grime that it leaves behind on the board in the flux. So oh, did Winamp quit? Did. Uh-oh. My audio do its stupid thing. Okay, there we go. My audio out did its stupid thing where it stops working. Alrighty. So those are all in. Drop the excess on those. I think the rest is good. Okay. Alright, the little blinking lights need to go away for a minute because I need to steal them for the USB power. Oh. I need to install the chip and the jumper and this thing first. So it comes with a nifty little cap that snaps onto the button to give you a bigger thing to press on. A PIC microcontroller, pre-programmed with the software, and I lined up the little notch on the socket with the notch on the board, and I'm lining up the little notch on the chip, notch on the socket, firmly press it in. According to the instructions for testing an outside signal, it's got to be on one in the upper position. If I was putting a crystal in the crystal tester, I'd put it there. So we're going to put it there. Alrighty. Okay, so we are going to kill the blinky lights. And you're going to power this up, and which one should turn 0? Fourth digit tube display should read 0 when I power this up. Hey, look at that. Not sure what the button does yet, but let me grab my leads for the signal generator. Which are a simple BNC to alligator clip. You can't see the frequency generator where I have it sitting, unfortunately, but I have it set for 1.007 kilohertz. I could probably change it to be closer, but roughly a 1 kilohertz tone. Wow. That is super stiff. Haven't used these in a while. You know what? Put that up there. What's up? Get me a screwdriver. We will screw them. Had some down. I'm not even sure what this is. It was some kind of sensor from work. I think this was a reed switch magnetic sensor. making it easier to clip on by putting some wires on it. Oh, and I just realized you guys won't be able to see my oscilloscope anymore because Windows 10 broke it. Yay, Windows 10. That. Outside of this thing's frequency range, maybe? Okay. I got 10 hertz. Okay, before measuring signal, please switch J1. Okay, so I got it in the wrong position. So that position is for the frequency counter. Okay, let's try upping the volts peak to peak, maybe? Maybe it doesn't like a... Let's try a square wave. Voltage regulator's getting a little warm, but nothing else is getting warm. You know what? Let's try a TTL signal, which is 5 volts peak to peak. Hey! Okay, so this thing likes a 5 volt peak to peak signal. And that's pretty bang on. I am sending it 10.73 kilohertz right now. And it's reading 10.73-ish. Let's go back to 1K. Oh, you can barely see it. So I'm feeding it a 1 kilohertz tone. Well, a 1.010 kilohertz tone. And you can see it's staying pretty there. Let's see if it'll do all the way up to 10 meg. Huh. It's gonna take it a minute. Wink. Wow, it'll do a 1 hertz. See if it'll do less than a hertz. Okay, I'm feeding it a half a hertz. Okay, so it doesn't do less than a hertz very well. Wouldn't expect it to. So now I'm feeding it a 4 hertz tone. I wish you guys could see the screen so you... Okay, something's oscillating. I'm getting a buzzing noise. I don't know if the microphone's picking it up or not. But I may have hit the resonant frequency of one of those ceramic capacitors because I started hearing a 5 hertz tone. Do we really want to subject Mr. Wells to a biohazard like that, Lady G? I mean, I know he is the Duke of Terribleness, but... Okay, that's roughly a 10 hertz. Which will be 1 hertz. Order of magnitude up. 100 hertz. Oh, if you're in the Adriatic Sea, then you're the Sultan or whatever. Sultan of Terribleness. Okay, 1K. 10K. 100K. Well, 98.6K. Let's see how it does with a sine wave. Does pretty good with a sine wave. How does it do with a triangle wave? Does pretty good with a triangle wave. Now let's see here. Again, you won't be able to see this unfortunately because Windows 10 broke the software that allows me to view my Rigel scope, and Rigel has changed the way they do things, so they don't even really support my scope anymore. See, my my Rigel is outputting a square, or my signal generator is outputting a square wave instead of a sine wave. Oh, it's because it's the TTL signal out. So we'll set this to about 5 volts out. I forgot I was running a TTL, the TTL signal. Okay, it doesn't do as hot. Okay, so I am feeding it a 1 kilohertz sine wave right now, which it's a little bit dirty, it's jittery, but that might be capacitive load thanks to this thing. See how it does with the triangle wave. Better with the triangle wave. Again, my triangle wave, or my sawtooth, looks more like a sine wave right now, except for its peaks. But if I do a square wave, it's bang on. Okay. So, all in all, it was a nice little kit. We will shut that off. I will put my cap back on my TTL output over here. It has its quirks. Like I said, it doesn't do sine wave or or sawtooths very well, but it does do square waves pretty good. And my plant's taking over. My plant insists on being in the shot as usual. You're all just gonna have to live with it. Okay, so Mr. Wells, I'll explain a little bit here for you, since other people might not know what I'm talking about. I think I had a little one run in and run away. Okay, so let me clear some space out here really quick. Oh, okay, I'll leave the plant there then. Anyways, so Mr. Wells, what we've got is you've got your typical sine wave. This will be your 0 volt line. Your sine wave will go like this, and it'll be nicely curved. A sawtooth will ramp up quickly and then drop, and then ramp up and then drop, and then ramp up and then drop, and ramp up and then drop. They're supposed to look like the teeth of a saw blade. But more usually what happens, instead of a nice straight line, you'll get a curve. Unless you have a really good sawtooth generator. And then a square wave is, it'll go high for a time, and then drop low, and then go high, and then low, and then high, and then low, and then high, and then low. Like that. Thus the name square wave. And this frequency counter does good on the square waves, does okay on the sawtooth. It was off by about 300 hertz. it was reading 700 hertz when I was feeding it 1 kilohertz. So, and then it was reading 20 hertz when I was feeding it a 1 kilohertz sine wave. So, yeah. So we're almost done with this though. Got a little cleanup to do. Just isopropyl alcohol, 91%. Pick it up at your local pharmacy. And an old one of my toothbrushes. And this gets all that excess flux from the solder off, because flux can be corrosive if left on circuit boards. I forgot to clean off our audio board too after it was done. And I get a rag. This one just happens to be a microfiber cloth. Wipe it down so there's no residue left behind. And then just feel the board. If it feels sticky, then it's still got flux on it. The other 9% should be water. Yeah, the other 9% is water, Spoon. I just use the 91% stuff because it's that's the strongest stuff that you can get over the counter here in the United States without ordering it from a chemical supply company. Because you can get up to 99, or I think the most you can get is 99.99% isopropyl alcohol. But you've got to go to a chemical supplier for that, because that's considered lab grade. Still a little bit of sticky on there after I cleaned it off, so. Okay. And there we go. It's nice and clean on the bottom. It's not sticky anymore. Where'd my screwdriver go? I'll take my test leads out. We probably don't need you anymore, so I'll shut you down. Then comes the joy of unwrapping all the acrylic. Comes with these nice acrylic pieces to cut to build a case around it, but there's only one thing about this acrylic. As you can see, still got the protective film on it. Set that aside. And that's always the fun part of this CNC cut acrylic, is getting the paper off. Nice and clear acrylic. The protective paper did its job. It's not scratched anywhere. Alrighty. Let's look at my bag of hardware and see if I can figure out what goes where. Well, obviously I've got 4 long screws for the 4 corners. And they're going to need 4 nuts. And I have 4 short screws, which are going to be for mounting the board. How many nuts do I have for them? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay, so what I think is going on here is we're short 1 nut, it looks like. Mike, I need your nut. So it looks like in this case what you do is you kind of build standoffs with these. And that sits down on there like that. Actually, they might have given me 3 extra nuts. This one I'm having trouble getting in there with my fingers to spin it, so I'm spinning it with a pair of pliers. Okay. Board secured in. I will do one more thing. I will peel this protective film off the dot matrix. And again, more just peeling paper off of this acrylic. This is actually going surprisingly well. Typically when I'm doing this, it's usually a pain in my... Well, I say that, and now this one's doing exactly what it usually does, and that's... It doesn't want to come off in one piece. It keeps tearing. There we go. And this one... side with the power jack. Oh, you know what? There's one test that I didn't do on this. So I will have to power this stuff back up. Once I get the case assembled, there's one more test that I wanted to do. And that's, I wanted to vary the duty cycle and see how well it handles varying duty cycle. Duty. I mean, I'm not expecting a whole lot from this, but I am I wanted to see what it's capable of. Yeah, I'm not expecting a whole lot with the varied duty cycle because of, we already saw that it doesn't do well with anything other than a square wave. But let's throw it a square wave that's has a different duty cycle. And with the square wave and the sawtooth and all that, there's a circuit that you can, there's a buffer circuit that you can build and put on the input of this thing to turn that, to turn the sawtooth and the sine wave into a square wave. So again, so far all these acrylic pieces have been fitting together nicely. Paper does what paper typically does on these, though, where it doesn't come off all in one sheet. But I've come to expect that from acrylic, so I can't fault the product. Yeah, all the sides are in. Yeah, sure, I say that they're all fitting together nicely, and and then the top doesn't want to go on. Alright, yeah, it went together okay. It took a little finesse. That piece of acrylic is just a hair too long and getting in the way of the screw, but I was able to work it past it. Now you don't want to tighten these down too tight because you'll crack the acrylic, because there's not a whole lot of meat on these corners. I'm just tightening them down until they start spinning. And there we go. There it is, finished. We're going to do that one last test really quick. Again, like I said, I don't expect it to pass this with flying colors after its performance with sine waves and sawtooths. But you never know. Okay. I need the power cord again. That is a sine wave. Let's put it back to a square wave. Okay. So I'm putting out a 1.012 kilohertz tone in a square wave and 1.012, but I'm doing it at a 50% duty cycle. There I am doing it at a, I'd say probably a 5% duty cycle. And there is a 95% duty cycle. So, I'm varying the duty cycle and I'm watching my output as well as it on the oscilloscope, and they're actually matching up pretty well. So all in all, this is actually a pretty good little frequency counter. So it doesn't do sine waves and it doesn't do sawtooths very well, but you know, that's difficult for a frequency counter to do in of its own. You almost need the math function, a frequency counter built into an oscilloscope in order to get any good frequency counts on a sine wave or a sawtooth. But this is actually, all in all, a good unit. Again, this is Banggood Item 106-3307. Their little, they call it a frequency tester, but it's a frequency counter. It's a nice little do-it-yourself kit. It goes together fairly easy. You guys saw me. It took, complete with testing, 1 hour and 40 minutes to assemble it. I'll have to read up on it to figure out what this what the button does, but I believe that's I can generate frequencies from it, and then I'll have to play around with that and maybe come back and show you guys off on that. But it does not tell me anything about that in the instructions, which is a downside of some of the Banggood items, is you don't always get instructions. This one at least gave you the basics of start here, and you know, this pin has to be in this position if you're testing off of the leads. It has to be in the up position if you're plugging a crystal in, which I don't have any crystals to test. Otherwise, I'd put one in there for you guys. Alrighty, so that is going to be it for this Banggood item.